Hello students, in continuation with our series on case studies question, today we are going to take up questions on magnetic effect of current and magnetism. In our first discussion on case studies series, we have discussed what are case studies questions, why they have been introduced there in the syllabus and in the question paper, how we should prepare for case studies questions, and what is the proper way to answer such questions there. We have taken few sample case studies questions. After that, we have started chapter-wise case studies questions. First, we have taken electrostatics. After that, we have taken current electricity. And in that sequence, today we are taking questions on magnetic effect of current and magnetism. So let's take first case study on magnetic effect of current and magnetism. A moving charged particle will experience electric force Fe equals to QE and magnetic force Fm equals to QV cross B. Net force on the charged particle is given as F equals to Q E plus V cross B. Depending on the directions of E, V and B, various situations are possible and the motion in general. Now, let's take what are the different questions given on this case study. First question is, an electron moves with a velocity v in x direction. An electric field acts on it in y direction. The force on the electron acts in. Now remember, if you have a charged particle moving in the region of electric field or magnetic field, it will experience force. The force on the charged particle in electric field is given as your F equals to QE. Now, since we have the electron here, in that case, the force experienced by the electron, since it has negative charge, so we can write it as your minus QE. It means it will be acting in opposite direction to the electric field which is acting there. So since electric field is in the y directions, so obviously the force on the electron will be in the negative direction of y axis. So B is the correct option. Let's now take the next question. Lorentz force is, first one is electrostatic force acting on a charged particle. This is wrong. Magnetic force acting on a moving charged particle. That is called as the Lorentz magnetic force. Then is the vector sum of the electrostatic and magnetic force acting on a moving charged particle. This is the correct one. The vector sum of the gravitational and magnetic force acting on the moving charged particle. This is wrong. So obviously in this case, the third one is the correct option. Next one. A certain region has an electric field E equals to 2I minus 3J Newton per Coulomb and a uniform magnetic field B equals to 5I plus 3J plus 4K Tesla. The force experienced by a charge 1 Coulomb moving with velocity I plus 2J meter per second is. Now, if you consider here, since it is now the Lorentz force acting on it, because there is the electric and magnetic field both, so F will be equals to QE plus V cross B. Now here, if you consider now a force due to magnetic field, it is given as your F QV cross B. So Q is your 1 Coulomb, so it is your 1, and for V cross B, we can take a cross product and we can find its value by expanding the determinant. So it is your I, J, K, and the velocity is your 1, 2 and 0. And for the magnetic field, it is your 5I plus 3J plus 4K. So it is your 5, 3 and 4. So we'll expand this determinant, and if you expand this, for I it will be your 8I. Then it is for J, it is your 5 into 0 minus 4. So it is your minus 4J. And for K, it is your 3 minus 10. So it is your minus 7k. So this is the force on the charged particle due to the magnetic field. Now, if you take the net force, charge is your 1 coulomb, so it is your 1 here, and electric field, this is given as your 2I minus 3j, and for this one it is your 8I minus 4j minus 7k, and this, if you consider, this is your 2 and 8, so it is your 10I minus 7j and minus 7k. So this is the force acting on the charge of 1 coulomb. And now let's see the different options which are given. First one is your 10I minus 7j minus 7k. So the first one is the correct option here. Next question. A proton moving with a constant velocity passes through a region of space without any change in its velocity. If E and B represents the electric and magnetic field respectively, the region of the space may not have. Now here it is given that the proton moving with constant velocity pass through the region of electric and magnetic field without any change in velocity. So if electric field is not there, magnetic field is not there, in that case it will not be experiencing any force. But here it is given that the region of space which may not have. So this is possible. It can have motion there without affecting its velocity. So it's more, it will be moving with constant velocity there. So this is possible. E is 0 and B is not 0.
If the electric field is 0, but magnetic field is not 0, the electron might be moving in the direction of magnetic field. So in that particular case, it is possible that as there is no force acting on the charged particle due to the magnetic field, so there will be no change in its velocity.
E is not 0, but B is 0. E is not 0, that means electric field is acting there. B is 0. So due to that, there will be no force experienced by the charged particle due to magnetic field. But electric field is acting. But it is there that if electric field is acting there, definitely no matter in which direction it is moving, it will definitely have its velocity affected there. So in that particular case, it cannot move with constant speed. So that means this is the correct one. Electric field is not 0, B is not 0.
So it is possible that the force due to them are in opposite direction and net force on the charge is 0. Hence, the charge can go without any change in velocity. So this is also not the correct option.
Let's take now the fifth question. A charged particle with velocity 2 into 10 to the power 3 meter per second passes undeflected through a region of crossed electric and magnetic field. Magnetic field is 1.5 Tesla. The electric field intensity would be. Now, if it is passing through the region of the crossed electric and magnetic field, it can go undeflected if the force experienced by the charged particle due to electric and magnetic field is equal and opposite. So you can take QE equals to QV, and since it is a crossed one, in that case we can take a sine pi by 2 here, and in that case E will be equals to VB. So it is asked what is the electric field acting there. So velocity is given as your 2 into 10 to the power 3 and magnetic field is given as your 1.5 Tesla. So it is your 3 into 10 to the power 3 Newton per Coulomb. So if you see the different options, third one is the correct option. Let's take a second case study question. Ampere's law gives a method to calculate the magnetic field due to a given current distribution. According to it, the circulation B dot dl, integral over closed surface of the resultant magnetic field along a closed plane curve, is equal to mu naught times the total current crossing the area bounded by the closed curve provided the electric field inside the loop remains constant. Ampere's law is more useful under certain symmetrical conditions. Consider one such case of a long straight wire with circular cross section, radius R carrying current I, uniformly distributed across its cross section. Now in this particular case, if you consider, here it is given that it is this particular cross section, or this is a conductor there which is carrying current I, and this is through a conductor whose radius is R, and the current is distributed uniformly over its cross section. So current is passing through this and its radius is R there. Magnetic field at a radial distance R from the center of the wire in the region R greater than R, carrying current I. So here for this particular case, if you consider, this is suppose a conductor which is carrying current I and radius is R. We want to find at a distance R. So we'll construct an Amperian loop here. And if you take B dot dl, integral over closed loop, this is your mu naught into I. Now, so this is your B into 2 pi R and this is your mu naught I. So B will be equals to mu naught I by 2 pi R, because here R is greater than R. So if you look at this different option, the first one is mu naught I by 2 pi R. So this is the correct one. So next is there magnetic field at a distance R in the region R less than R. This is your R. And now we want magnetic field here at a distance R which is less than this R. So in that case, that means our Amperian loop will be somewhere in this one. So this is the Amperian loop here, radius is R. So for this particular case, if you consider that if we apply Ampere's circuital law, then it is your B dot dl, integral over closed loop. This is your mu naught into I. I will be the current enclosed by this Amperian loop here, or inside the Amperian loop. So we'll have to take current enclosed in this particular section. So it is your B into 2 pi R as it is. Now mu naught, what is the net current? Because entire current I is now not passing through this small loop which we have taken there, or the area enclosed by that small loop. So it is your I divided by pi R square, a current per unit area of cross section, and this multiplied by this area, that is your pi small r square. So here if you consider, R will get cancelled, 2 pi will get cancelled. So B will be equals to mu naught I R divided by this 2 pi R square will be there, because here pi will get cancelled and this 2, suppose it is coming in the denominator, then it is your 2 pi R square. Here it is your I into R in the numerator there. So if you look at this different options which are given, first one is wrong, mu naught I by 2 pi R, mu naught I R square divided by 2 pi R capital R square, that is also not correct. So here it is the fourth one which is the correct one. So in that case, this is the correct option, mu naught I R by 2 pi capital R square. Let's now take the next question. A long straight wire of circular cross section, radius A, carries a steady current I, and the current I is uniformly distributed across the cross section. Which of the following plot represents the variation of magnitude of magnetic field B with distance R from the center of the wire? So now in this case we have seen when a small r was less than capital R, then B was varying directly to R, and for the case when it is having a distance small r, which is the distance from the axis, more than radius, in that case it was varying as inversely. So if you look at the diagram, the first one is the correct one, because second one is wrong, this is also wrong. So the first one will be the correct option. Let's now take next question. A long straight wire of radius capital R carries a steady current I, which is uniformly distributed across its cross section. The ratio of magnetic field at R by 2 and 2R. Now we have this particular distance R by 2 means it is inside, and for the other case it is your 2R, which means the point of observation is outside. So in that case here, if I consider magnetic field, if it is B1, it is your mu naught I R, this was your divided by 2 pi capital R square for inside case, and for outside it was your mu naught I divided by 2 pi R. So now in first case it is your R by 2, in second case it is your 2R. So if I take the ratio, mu naught I will get cancelled, 2 pi will get cancelled. So in first case it is your R by capital R square, and this R for first case it is your R by 2 divided by R square. For second case this R, it is there in the denominator because we are taking B1 by B2, so it will ultimately come in the numerator, and this small r now is your 2R. So in that case it is your 2R here. So this, if you consider this R square, this R square by R square will get cancelled, 2 will get cancelled, so it will be 1. That means the ratio will be 1:1. So that means here, if I consider the fourth one is the correct option. A direct current I flows along the length of an infinitely long, straight, thin-walled pipe. Then the magnetic field is. Now, in this particular case, it is a thin-walled conductor. So it is like this, which is carrying current. So that means the current is basically passing through this particular section, this particular part. Now, if you look at the different options which are given, it is uniform throughout the pipe but not zero. So this is not correct. It is zero only along the axis of the pipe. So this is not correct. Even if you consider the points here, in that case also it will have the zero value there. Zero at any point inside the pipe. This is correct. And let's take the maximum at the center and minimum at the edges. This is wrong. So that means the third one will be the correct one. Just see the 2. Magnetic field is definitely zero there, even along the axis of the pipe. But it is said it is zero only along the axis. This is wrong. Anywhere inside this one hollow part there, it will be zero because it is not enclosing any current there. So Ampere law, if you apply, B dot dl will be equals to mu naught into current enclosed. Current enclosed is 0. So in that case, it will be 0 there. So the third one will be the correct option. Let's now take the third case study question. An electron with velocity v0 very less than c moves in a circle of radius r0 in a uniform magnetic field. This electron is able to traverse a circular path as magnetic field is perpendicular to the velocity of electron. A force acts on the particle perpendicular to both v0 and b. This force continuously deflects the particle sideways without changing its speed, and the particle will move along a circle perpendicular to the field. The time required for one revolution of the electron is t0. This is what they have given, and the diagram which is given, this is the circular path, this is the magnetic field B which is acting there. It is moving the circular path there. Magnetic field is indicated that it is acting perpendicular to the plane of the paper here, it is shown cross, so that means it is acting into the plane. So at every point, if you consider, definitely the force will be acting perpendicular to the velocity and magnetic field because it is cross product of V and B. So the path will be circular there because velocity is perpendicular to the magnetic field there. Now let's take the different questions which are given on this one. So the first question, the speed of the electron is now doubled to V naught. The radius of the circle. Now if you consider the force which is acting on the charged particle in the magnetic field, this is your QVB sine pi by 2, and this is equal to the centripetal force there, that is your mv square by r. So here V will get cancelled, so that means R, if you consider, this is given as your, this R is coming here, so it is your mv by qb. So this you can see that R will be proportional to V. So here, if the velocity is doubled, definitely this radius will also change. That means the radius will become double. So the second one will be the correct option there. Let's now take the next question. If V naught equals to 2 times V naught, we are doubling the speed. The time required for one revolution of the electron will change to. Now here, we have taken the expression for the radius here. Now let's take the time period. This is your 2 pi r by V, velocity. Now for radius, if I am putting 2 pi, r is your mv by qb, and this V is also there in the denominator, 1 by V there. So in that case, V will get cancelled, and now it is your 2 pi m by qb. Now you can see that this does not depend upon the velocity. The time period will be independent of the velocity and also on the radius of the circular path also. So in that case, it will remain T naught, because it was mentioned there earlier in the statement there that time period of revolution of the electron is your T naught. So in that particular context we are taking, so in that case it will remain same, so it will be the third option, which is the correct one. Third question. Charged particle is projected in a magnetic field B equals to 2I plus 4J into 10 to the power 2 Tesla. The acceleration of the particle is found to be xi plus 2J meter per second square. Find the value of x. Now here, this is a bit tricky, because if you try to find the expression of the acceleration by taking up force divided by mass there, but for force you do not know what is the expression for the velocity there. So here one thing is obvious. If it is moving in the magnetic field, in that case, no matter in whichever direction the velocity is there, the force will always be perpendicular to the velocity and magnetic field. So that means if I consider that the force is perpendicular to the velocity and magnetic field, it means acceleration is also perpendicular to the magnetic field. It means this acceleration which is given and the magnetic field, they must be perpendicular. And if they are perpendicular, then A dot B will be 0. Dot product will be 0. So if I consider it is the dot product of xi plus 2j, and then it is your 2i plus 4j, this is 0. 2x plus, this is your 2 into 4, that is 8 equals to 0, and that implies that x value will be equals to minus 4. So here if you consider the value of A, it will be your minus 4. That means B is the correct one. Next question. If the given electron has a velocity not perpendicular to B, electron is not moving in perpendicular direction to the magnetic field, then the trajectory of the electron. Now, if suppose the charged particle which is moving in the region of magnetic field, if it is having velocity perpendicular to the magnetic field, the path is circular. If it is moving in the direction of magnetic field, it will be a straight line. But if it is making some angle with the direction of the magnetic field, like here this is the magnetic field and the charged particle has velocity v in this direction, in that case the path will be a helical one. So in that case, this will be the correct option there, that is C. Now why it is helical there? If you consider the velocity, this is your v and this is your b. Velocity we can resolve in two components. One is suppose perpendicular, v perpendicular, and another is your v parallel. If I take the angle is theta there. Now v parallel, which is there in the direction of magnetic field, due to which the charged particle will go undeflected there. It will move in the direction of magnetic field because it is not experiencing any force due to magnetic field. It will describe a translational motion. But if you consider the v perpendicular, since the velocity is perpendicular to the magnetic field, the path will be circular one. It will describe a circular path. At the same time, it will have the translational motion also. So the actual path will be helical one. The next question. If this electron of charge E is moving parallel to the uniform magnetic field with constant velocity v, the force acting on the charged particle. Now, we know that if it is force on the charged particle, it is given as your qv cross b. So here, magnitude wise, if you take qvb sine theta, and since it is moving in the direction parallel to the magnetic field, so theta term will be 0. And if theta is 0, that means the force will be 0. So the fourth one will be the correct option. These were some of the case studies questions on magnetic effect of current and magnetism. We'll continue with few more case studies questions on magnetic effect of current and magnetism in our next discussion.